Creating the equation of a piecewise function from a given graph will require the same skill set as if we just had a regular function that was not in a piecewise form. In this example, we have three separate pieces that make up this function. You'll notice first that there's a section of the graph that does not have any points in it. That part right there is going to need removed from the domain. The numbers from -7 to -4. You're also going to notice that there are no circles on the ends of these line segments, indicating where one of them stops and one of them starts. We're going to assume for the purposes of this exercise that all of the endpoints exist. Now, if you're looking carefully, you'll notice that there is one endpoint that we need to deal with, and that's this overlap over here. In that case, we're going to assume that this is the open circle and that the black line segment will have the closed circle. So all closed circles with the exception of that one place. Lastly, we're also going to assume for this exercise that we do not go beyond the ends of this graph. So we are going to be looking entirely in the space from -10 to +10. It might benefit us, as we did in other examples in previous lessons, to begin by setting up the domain for each one of the three pieces. So this first blue piece, its domain goes from -10 to -7. So I'm going to write my function so that the first piece goes from -10 to -7. The second piece, skipping that space we identified as not having any functional values to it, looks like it goes from -4 to +4, and that is where we wanted to include that endpoint. So for the black function, we're going to go from -4 up to +4. And for the red function, we're going to start right after 4, and we're going to continue all the way until x is 10. So we'll start right after the 4, not equaling the 4, and we'll go up to including 10. You need to be careful when writing the equations for linear pieces of piecewise functions because a lot of the skills that we have for writing the equations of lines doesn't jive perfectly with already being in the f of x, y equals version for any piecewise function. And I'll show you what I mean. Let's start by looking at the blue line segment. We've got a point here at the point -10, 3. And we've got a point down here at what looks like -7, -6. Determining the slope between those 2 points is a matter of walking out our slope triangle. So we moved down 9 and over to the right 3, which tells me that we have a slope of -3. I've got 2 points. This line segment does not have a y-intercept. It has an x-intercept, but it does not have a y-intercept. So we can write the equation in point-slope form. And if I tried to enter this as the functional value for the piecewise, you'll notice that redundancy in the y, that I have a y here, and then there's another f of x / y over here, which really doesn't work for me to just write that point slope form in there. So I really want to go through the algebraic effort of putting this into slope-intercept form. If I go through the trouble of putting it in slope-intercept form, then I'll have a version, this block right here, that I will be able to enter directly into my function. You'll also notice when using this that you want to make sure that this y-intercept would technically make sense. If I was to continue this, I could imagine this line crossing somewhere way down by -27. That seems to make sense if I was to continue that. So there we have our first section based entirely off of the linear algebra or the linear skills that we already have. Now let's look at the black line that's in the middle. For the black line, we already have a y-intercept of 0, 0. So this one's going to be a little bit easier to write. I need to identify one other point, and it looks like right here I'm at -4, -3. I walk my slope triangle, I go up 3 and over 4. So my black line has a equation of y equals 3/4 of x. Normally, I would write the y-intercept at the end of that plus whatever it is. Don't need to do that because the y-intercept is 0. So my second part is y equals 3/4 of x. Moving on to the last section, to the red section, I'm going to do something similar that I did with the blue. We're going to identify 2 points that are on the line and work with those 2 points. Now, this, despite the fact that that point is not technically there, the point 4, 0 is technically not there. That is where my line heads to. We call that the bound of the end of the line, or the bound of the line. Because my line is headed there, I could still treat that as one of the points, because I know that that line would be there if the line would, or I know that that point would be there if the line was to continue. So I can start with that point as my first point, 4, 0, and then I'm going to need to find another one somewhere else. And it looks like I have a candidate over here at 10, -4. Walking my slope, I'm going to go down 4 and over 6. So down 4 and over 6, which means I have a slope of -2/3. Writing my point slope form again because I do not know the y-intercept. Y minus 0 equals -2/3 x minus 4. Y equals -2/3 x plus 8/3. And that's my final version of my red line. I add that to my piecewise, and I have a complete piecewise function. Before leaving this example, it's worth mentioning the range of this example. If I clear out all of my drawing, you'll see that we have a low end of the line segments right here, and you'll see that we have a high end right here that matches this high end here. Before we write our range, we want to make sure that we cover everything that's in between those two high end and low end. Thanks to the blue line segment, I get everyone. The black line segment gets almost all of it. The red line segment gets a little bit less. But because this blue line segment has the bottom and the top on it, I see that I cover all of the values of the range. So the top looks like it's at 3. The bottom looks like it's at -6. I've got values on both of those endpoints. So we're going to say our range is -6 to +3.